pressure and what is known as kinetic molecular theory. That's going to be the topic of this first lesson in a chapter on gases. And we've got this chapter on gases, the next one will be on solids and liquids, and after this lesson we'll have a variety of gas laws spread out over the course of the following 2 lessons. Now, this lesson is part of my high school chemistry playlist, and I'm releasing these lessons weekly throughout the 2020-21 school year. So if you want to be notified every time I post a lesson in this or any future playlist, subscribe to the channel and click the bell notification. All right, so once again, this is the first lesson in the chapter on gases, and the next chapter is going to be covering solids and liquids, and just want to make sure you realize some comparison contrast between solids, liquids, and gases. So a gas has no definite shape and no definite volume. It will fill up any container you stick it in, so it will expand its volume, it will contract it, you can compress its volume, so on and so forth, and it'll take the shape of the container as well. So no definite shape, no definite volume. And we can contrast that with a liquid, because a liquid's going to have a definite volume, but it will take the shape of whatever container you put it in. So no definite shape for a liquid, but there is a definite volume. And then finally for a solid has both a definite shape and a definite volume. So that's kind of compare and contrast your 3 different phases. But for a gas, again, no definite shape, no definite volume. And this no definite volume ultimately belies the fact that a gas is fairly compressible. Now, you can squeeze a whole lot on a liquid or a solid and it ain't going to move much. But for a gas, they can be compressed to much greater degrees. And the truth is, it's because a gas is made up of mostly empty space. And this is, kind of weird. So, but you got these lovely molecules or atoms. Noble gases would be just atoms, but for the rest of them, just be molecules. And these molecules are spread out by a fair amount of empty space. Whereas in the liquid or solid phases, those molecules or atoms are actually in contact with each other. They're touching each other. Now, the weird thing is that it turns out, so if you take this a little further, and we talked about this earlier in the course, that atoms themselves are actually made up of mostly empty space. But in a gas, the atoms are spread out by a fair amount of empty space independent of the atoms themselves. And so it turns out a gas is made of mostly empty space, but the more pressure you put on them, the less empty space you're going to have, because you're going to force those molecules or atoms to get closer and closer together. And so pressure is something we talk about with respect to gases in chemistry, but not so much with solids and liquids. Now, it's not that it's not important. If you're an engineer or you're talking about physics or something, you still might talk about pressure in the context of liquids or solids. But in chemistry, it's not the most relevant thing. So we'll talk about pressure here in this gas chapter. We will probably not talk about it in the liquid or solid chapter. So pressure, it turns out, is a very mathematical definition. It is force per unit area, so force divided by area. So if I wanted to cut a steak, let's say, a nice thick, let's go ribeye steak, and nice thick ribeye steak with a dull knife. Should I press soft or should I press hard? So, and definitely I should press hard. The harder you press, the more likely it is to cut and stuff like this. And that the idea is that pressure is directly proportional to force. And so the more force you apply, so the greater the pressure it generates, in this case on that steak. Now, if I really want to cut this, steak, I should probably just switch out the knife, get rid of the dull knife and use a sharper knife. And the idea of having a sharper knife, what that really accomplishes is it reduces the surface area over which the force is applied. And it turns out here, so pressure is directly proportional to force, but pressure is inversely proportional to the surface area over which is applied. And so with that sharper knife, a smaller surface area leads to a greater pressure. And so higher forces but smaller surface areas both lead to greater pressures. And if the pressure is great enough, it will slice right through that ribeye steak. Cool, so that's pressure. Now, if you look at SI units here, so the SI unit for force is newtons, and for area would be meters squared. And a newton per meter squared here is what we call a Pascal. And so the Pascal is the SI unit for pressure, and that's great. And if you're taking a physics class somewhere along the way, you'll probably use that quite a bit. However, we don't like using this unit. It's not the most convenient one, and for historical reason, it wasn't commonly used back in the day. And so to this day, we don't use it commonly in chemistry. It's possible, but much more likely you're going to use what are called atmospheres. So an atmospheres is just atmospheric pressure at sea level. Now, they've got to define it at sea level. It turns out that your pressure at sea level is due to the weight of all the gas above you in the atmosphere. And so notice once you get to outer space, well, then there's no gas above you in the atmosphere, and the pressure effectively goes down to zero, and you're in a vacuum out in outer space, so to speak. Now, turns out in outer space, you really do have a random molecule every once in a while, but they're so dispersed that, again, for all practical purposes, your pressure really is zero. You're almost in a complete vacuum out in outer space. Now, At sea level, again, you got a huge weight of gas, but as you travel further and further up, even within the atmosphere, you're going to have a lower weight of gas weighing down on you. And so as you go up in the atmosphere, you're going to find the pressure gets less and less and less until you reach essentially outer space where the pressure goes to zero. And so that's why they got to say that 1 atmosphere is the pressure in the atmosphere at sea level specifically. So this will kind of have some profound impacts that we'll see in later chapters when we talk about how pressure decreases as you go up in the atmosphere at higher elevations, you might say. So, all right, so the Pascal is the SI unit, but it's not really the one we're going to largely use. The most common one will be atmospheres. So we'll find out this is by far the most common one used in chemistry, but there's a couple others you really need to know. And one of them is called the millimeter of mercury. And it turns out, it's not that. Let's try that again. So that an atmosphere is equal to 760 millimeters of mercury. Now, mercury is a really dense liquid. It's 13.6 times more dense than water. And it is used in a variety of old school pressure apparatuses like what's called a manometer or like a barometer. So, and idea is that, you'll actually have differences in pressure pressing on 2 sides of something and causing 2 levels of mercury to be unequal. And it turns out if you have 1 atmosphere pressing on one side, but a vacuum on the other side, the difference in those fluid levels will actually come out to 760 millimeters when you have that 1 atmosphere pressure difference. And so that's where this kind of equality comes from. So it turns out they invented a new unit called the torr. So it turns out this 760 millimeters of mercury is dependent on Earth's gravity. And so they wanted to kind of get something that's independent of Earth's gravity. And so they went to the torr. And so as long as you're on the surface of the Earth, millimeters of mercury and torr would be the same thing. And so 1 atmosphere also equals 760 torr. And you're pretty much almost on, I don't think you're likely to ever see anything other than at the surface of the Earth. And so millimeters of mercury, torr, treat them as synonymous for this class. And then finally, if we went over to the actual Pascal, which most likely you're probably not going to have to do, but you never know. So it turns out 1 atmosphere equals 101,325 Pascal. So roughly 100,000 Pascals, a nice rule of thumb. And so because this is such a large number, sometimes we'll turn this into kilopascal until you get 101.325 kilopascal. Cool. And like I said, it's really these first 3 that you need to know. And by need to know, I mean I'd actually memorize these conversions, that 1 atmosphere equals 760 millimeters of mercury and 1 atmosphere equals 760 torr, because you might have to convert back and forth. Now, the equations we're going to use in this chapter are almost exclusively going to use atmospheres in them. But oftentimes the pressure might be given to you in either millimeters of mercury or torr, and you'd have to convert it. Now, technically, they could give you a pressure in pascals, but I don't think they're going to make you memorize this number in any high school class. In fact, we don't typically make our college freshmen memorize that number either. However, in a physics class, you would use Pascal much more commonly than any of these other units. So if you're taking high school or AP physics or college physics at some point, be prepared. You might be seeing that at some point in time. So now we're going to spend some time talking about what is known as kinetic molecular theory, and some people call it ideal gas theory, and it's kind of just a theory about gases. So, and you'll hear us in chemistry talk quite a bit about ideal this, like an ideal gas or an ideal fluid or things of this sort. An ideal solution comes into play. And so the key is that the world truly isn't ideal. So, and the world is much more complicated than a lot of times the little mathematical equations we come up with and stuff like this. So, but oftentimes we'll try and just like simplify things to a certain level and come up with certain ideal situations. And so we do this for a gas. We talk about an ideal gas, and you contrast that with what's really happening in the world, and we call that then like a real gas or a real fluid or a real solution, things of this sort. So, but in this cast, we're going to exclusively talk about ideal gases, and you should just realize that real gases in reality often behave just a little bit different, or in some cases, in extreme conditions, very different. So, but we're going to talk about the characteristics that define what it would take to actually behave like this ideal gas that we're going to talk about throughout this chapter. And the characteristics are all defined by this kinetic molecular theory. And if you got your study guide in front of you, so they're kind of listed there for you, and they're not listed in the order that normally presented. So normally the fourth one on your handout there is the one I would present first. And I'm going to, but we'll find that I put the 2 at the top of the list there for a reason. So, but the fourth one is that, all the atoms or molecules of a gas so are in random motion, and there's a large number of them. So, and they're just random motion. So they're just moving around, and they might collide with each other. They might collide with the walls of a container. They're just in random motion all the time. So that is tenet number one, or characteristic number one of kinetic molecular theory. So some other things we want to talk about. So, and now I'll put the important ones on there. So, and I'm going to phrase them in kind of a shortened way here from what you see on there. So, but I'm going to say no molecular volume, just a nice short way to kind of summarize it. So, but if you notice, it says gas, atoms, or molecules occupy negligible volume compared to the space between atoms or molecules. And this goes back to what we said earlier, is that a gas is made of mostly empty space. The amount of volume that the atoms or molecules actually take up is negligible. Now, do the atoms or molecules really take up zero space? Well, not really, but it's just so low in comparison to the amount of empty space present in a gas that will just round it down to zero. So, and I'm saying that here by no molecular volume. And it's not that a gas doesn't have volume, it's that the molecules in the gas take up so little volume, we're just rounding it down to zero. So that's going to be our second characteristic, but I put it at first here because it's really important, as we'll see in a little bit. So, and then we're going to also say, we're going to say no attractive forces. Now, kinetic molecular theory actually says no attractive or repulsive forces between all the molecules in there. So what we'll find out when we talk about solids and liquids in the next chapter is that it turns out all molecules and atoms are at least a little bit sticky. They all have a little bit of attractive forces, and that's why I'm focusing on the attractive forces here. So there's no philosophy that says, well, all molecules are a little bit repulsive. Nope, they're all a little bit sticky. They all have a little bit of attractive forces at the very least, some stronger, some weaker. We'll find out. Well, to be an ideal gas, that can't be true for you. So we have to kind of ignore those. And so for an ideal gas, there are no attractive forces. Well, in reality, again, all molecules are at least going to have a teeny tiny bit at the very least. So that's why we're going to focus on these attractive forces. So, and it turns out these two are going to be the most important tenets, not because they're the most important for the theory, but they're just the easiest ones to test you on, as we'll see in a little bit. So third thing we'll see are elastic. And this is really kind of a physics illusion here. So when you take a physics class, you're going to learn that elastic collisions are one in which before and after the collision, there's no loss of kinetic energy. And kinetic energy is the energy of motion. So no net loss of kinetic energy during an elastic collision. And we contrast that with inelastic collisions where there is a loss of kinetic energy during a collision. So, but in this case, all the collisions are perfectly elastic. Now, it turns out when you actually study the physics of it, so you find out that what's the difference between elastic and inelastic? Well, in an inelastic collision, the two bodies that are colliding are going to have some propensity to want to stick to each other. Well, if we've got no attractive forces, then they're not going to have any propensity to want to stick to each other, which is why the collisions end up being elastic. So, but just another tenet here, and probably one of the lesser important ones here. We already said that a gas is composed of a large number of atoms or molecules in random motion. That's the fourth one. And I'm going to skip that one on the board. I have no way to really shorten that one, but we will put the fifth one on here. So here, this lovely little alpha looking symbol, it's not truly alpha, it actually is a little bit bigger than the alpha symbol and usually comes out a little further, but it means proportional to. And it says that the average kinetic energy of a gas is proportional to its temperature. You double the temperature, you'll double its average kinetic energy. And we gotta be careful when we talk about doubling temperature because we always have to talk about it in the Kelvin scale, doubling it on the Kelvin scale. So that Celsius scale, you never want to talk about doubling it there because somebody just looked at the freezing of water and said, I'm calling that 0. And just said, that's how we're going to make that Celsius scale work. And that's a little bit kind of a random choice, right? It's like saying that I'm 5'8", and I'm the standard now. If you're 5'8", you're now 0 on the Chad scale. Well, that's kind of a random place to just call 0, right? So notice if you were like 5'10", so then you'd actually be only 2 inches tall on the Chad scale. And if you were 6 foot, you'd only be 4 inches tall on the Chad scale. Well, if somebody who's 2 inches tall on the Chad scale, and you have somebody who's 4 inches tall on the Chad scale, you wouldn't actually say that the guy who's 4 inches tall is double the height of the guy who's 2 inches tall. Because it's not true, because the 0 here is not actually 0 of having no height. It's just an arbitrary place to put a 0 on the scale. Well, the same thing happened on our Celsius scale. Somebody again looked at that freezing point of water and just said, I'm calling that 0. Well, that wasn't the real 0. It's on the Kelvin scale that we actually have the real absolute 0 temperature, the complete absence of heat if you will. Celsius just has an imaginary zero, and so you shouldn't use that when you're talking about like doubling the temperature. It always has to be in terms of the Kelvin scale. All right, so kinetic energy on average, or the average kinetic energy of a gas is proportional to its temperature. It's important. So, and again, kinetic energy is that energy of motion. And so it turns out the only thing you need to know about a gas to know anything about its average kinetic energy is its temperature. As temperature goes up, molecules move faster. And so you find out that the average speed of a gas is also related to its temperature. It's not proportional, as we'll find out, but actually you'd find that out in a little more advanced class. So, but it's related. So turns out, as if you look at what's going on at the molecular level, as you raise the temperature on a gas, the atoms or molecules are just moving faster and faster and faster and faster. So, and we'll allude to this in a couple other places. It turns out if you actually want to look at the actual equation, so looks like this. Your average kinetic energy is equal to 3/2 RT, and it turns out it's, I'm oversimplifying this just a little bit. Turns out this is for like a noble gas, which we call a monatomic gas, which is beyond what we need. And technically, you don't really need this equation for high school. So, but you can see that the kinetic energy is indeed proportional to the temperature. You double that temperature, you double the kinetic energy. You triple that temperature, you triple the kinetic energy. And so the only reason I really include this equation is just so that it's a demonstration of the fact that kinetic energy is indeed proportional to temperature. Now notice we also have to call this an average kinetic energy. And the reason we have to do this is actually you have a distribution of speeds in your molecules. So you have, in any sample of a gas at any whatever temperature you're at, you're gonna have some molecules moving faster and some moving slower. And that's why we gotta look at an average. But you usually get a nice Gaussian distribution or something resembling a quasi-Gaussian distribution, not quite perfectly Gaussian. And so that's why you got to include this little average here. You can't just say kinetic energy because you don't just have one molecule in a sample of a gas. You've got zillions of molecules, and some again faster, some slower, and that's why this is related to the average. Okay, so the reason I put, again, these top two first is it tells us under what conditions, it gives us an idea of what would be necessary for conditions for a gas to behave ideally. So this kinetic molecular theory is just really the tenets of what has to be true for a gas for it to behave ideally, hence some people calling it ideal gas theory. And so if we look, ideal behavior right below on your handout there says gases behave more ideally at low pressures and high temperatures. So let's talk about that. So let's do that right here. So let's talk about low pressures. Why would a gas behave more ideally at low pressures? Well, at low pressures, the gas molecules spread out more. At high pressures, you're shoving them closer and closer together. And notice we said that the molecules in a gas don't take up any significant amount of volume. They have no molecular volume or they take up negligible volume. And that's most true when they're really spread out at low pressures. So the truth, though, is that if you jack up the pressure significantly in a gas, you'll actually force those molecules close enough together that this would be a terrible assumption. And so our kinetic molecular theory, our ideal gas theory, works best at low pressures. And it turns out it gets worse and worse and worse oftentimes at higher pressures. All right, so we're also told that gases behave more ideally at high temperatures. So and we just related kinetic energy to temperature, and so the higher the temperature, the faster the molecules are moving. And so think about taking two magnets, for instance. Let's say I just forced two magnets close together. So, and at some point, north to south, right? So at some point, they're just going to stick. So, but instead of just like gradually bringing them close together and let them stick, let's say I hurled them at each other at 100 miles an hour. And so at that kind of speed, they might just bounce right off each other. And so if you give them enough kinetic energy, it might overcome the attraction of the magnetism here and stuff like that. Well, same thing with the gas. Again, we said that gases have no attractive forces when they behave ideally, but we also said there's no such thing as an ideal gas. All gases have a little bit of attractive forces. But as long as the gas molecules are moving pretty fast, they wouldn't ever get to feel these attractive forces to any significant extent. They'd have enough kinetic energy to overcome those attractive forces. And when our gas is moving really fast? Well, at high temperatures. And so these are the two, this is why I put these two first, because it explains why gases tend to behave more ideally at low pressures and high temperatures. You could possibly see a question that says, under which of the following conditions is the gas most likely to behave like an ideal gas? And you'd be looking for some combination of the lowest pressure and highest temperature. Cool. So we're going to introduce what's called the ideal gas law in a little bit, and I'll give you just a little tiny bit of a preview here. So this is your ideal gas law, PV equals nRT. So, and the only reason I bring it up now, because we're going to bring it up really in the next lesson, but the ideal gas law, this law is the most accurate mathematically when a gas is behaving ideally. And so when is a gas behaving ideally? Well, at a combination of low pressure, high temperature. And so this lovely ideal gas law is really a simplified view. So real gases, it's not always exactly true, this mathematical expression, but at sufficiently low pressures and high temperatures, this works fairly well. So that's why I bring that up. One last other thing. So on your handout, you'll see that it says that gases behave more ideally when they have lower intermolecular forces. So, and you're going to learn about intermolecular forces in the next chapter. And so, but just kind of allude to that now. So, when gases are less sticky, so to speak, when they have these lower intermolecular forces that you'll study, well, the lower the forces, the more this lovely tenet of kinetic molecular theory would be true, and the more ideal behavior. And so, we'll revisit this again in the next chapter and allude back to kinetic molecular theory in that context.